Okay.
Cool. Let me know whenever I need to start. I can start.
I think you can start now.
Okay, great. Thank you so much.
No worries.
Is there any way you can set up the camera to look at the audience?
It's
Thank you so much.
it's very hard, but we try.
Cool. Thank you.
Yeah.
Amazing. Okay, let's get started. Let me share my screen. Can you see the slides?
Yeah.
Amazing. Sorry, some of us could not make it to Sydney because of various visa issues. So apologies for doing this virtually. But we are very excited to talk about this tutorial on efficient algorithms for leveraging LLMs for both predictive and generative Rexis models. We're a bunch of AI practitioners from LinkedIn. We'd love to share our experience in making LLM deployment and development efficient. And since we are a bit late to start, we will try to rush through some of the slides. But please feel free to stop me at any time if you have any questions. Feel free to post questions on Zoom chat as well. If you have any other questions. So this is the team that's prepared this tutorial. Of course, there's a lot more people that work on LLMs at LinkedIn, but this is the core team that built this tutorial, and most of us will be presenting today. Here is some published material. Some of our team members are authors of Liger kernel, which became really famous recently, which allows you to do efficient training, reduce memory usage, and has close to 5,000 GitHub stars. We have published several papers on quantization, alignment, and recently practical lessons on efficient AI for industry LLMs. And all of this material is also linked to the tutorial website. In case you want to go to the website, this is the QR code. So if you want to take a photo of this or take a screenshot, feel free to do that. All the material will be available on this website, and we'll also do a post-event questionnaire. And would love to get your feedback on the session. And if you have any questions or collaboration requests, please feel free to email us at aiafoptimization@linkedin.com. So this is the schedule for the day. So we'll talk about some intro and use cases for LLMs in the industry, followed by talking about efficient algorithms and efficient training. Then we'll go to the coffee break, which is, I think, 30 minutes, not 20 minutes. Following the break, we'll focus on inference optimization, including prefill and decoding optimization, pruning, and quantization. Towards the end, we'll do some closing thoughts and future work, and open to any questions. I know it's a little harder on Zoom to answer questions, but feel free to email us if Zoom is a little harder for you. We're very happy to chat with you. And we're also all, unsurprisingly, also on LinkedIn. So you can always text us on LinkedIn because we work at LinkedIn. So. Okay, now let's dive into the intro. So let's talk about some products which use GenAI at LinkedIn. So there is a product which allows you to change your profile summary, also create posts using generative AI. This has had huge success. And on the right, you can see new job seeker experience where you can ask an LLM a bunch of questions about a job. Are you a good fit for the job? Who works at a certain company? And essentially improve your job seeker experience. So these are two examples where we have successfully integrated GenAI into various products at LinkedIn. This is one of our more recent products where we enable a hiring agent for recruiters and job seekers. This particular workflow is for recruiters, where as a recruiter, you can automate a lot of the work you do. And now, of course, at the heart of this agent is one or more LLMs working on various aspects of the agent pipeline and essentially automating a lot of the busy work that recruiters have to do. And this busy work, once it's automated, allows recruiters to focus on higher level tasks. And as we speak, LinkedIn is building and deploying agents for other workflows as well. I'm not allowed to talk about some of them for confidentiality reasons. But TLDR is we are betting big both on LLMs and hiring agents, and agents in general, where hiring agent is an example. So these three takeaways, they're not super relevant to today's tutorial, but I still wanted to highlight them, is that Gen AI ecosystem, when you're building something which is based on LLMs, it requires a lot more than just LLMs. You need a whole ecosystem around them. And most importantly, you need domain adapted small language models, usually because a lot of these use cases require low latency, efficiency, lower costs, and quality at scale. So developing efficient or smaller models is very, very important. And as part of agentic workflows and similar things, you need LLMs as pieces of a puzzle, meaning that LLMs are stateless and you need to somehow integrate memory or personalization for you to have context-aware experiences, enjoy something that really works for your needs. But the dominating factor still remains, can you build models that are high enough quality and also operate at a low enough inference costs for it to be cost effective to you, and also for it to be of low enough latency for you for low latency use cases. So that's the part we will cover mostly in this tutorial, where we focus on how to make models as good as possible while make them as cheap to serve as possible. So of course, talking about use cases for ML and AI in the industry, this is no secret. Everything related to recommendations for e-commerce, some kind of email targeting, network growth, search, feed, all of these things require some sort of ML and AI. And for all of these use cases, what's happening now is that LLMs are slowly taking over each of these use cases. For instance, for recommendation systems, for so long, traditional models or DLRM kind of models were sacrosanct in terms of giving you the best accuracy possible. But now LLMs are also entering that domain, and we'll talk about some examples in a second. For search is moving towards navigational search or agentic search, for example, Perplexity or OpenAI's O3 model, where your search is now no longer boring. You can actually interact with an LLM and iteratively refine what you're looking for. So LLMs are slowly disrupting everything that I mentioned on this particular slide. So there are two key problem classes that we tackle at LinkedIn, and similar companies also do the same thing. One is more predictive in nature, where you focus on retrieval and ranking. Some examples of this are Meta's Generative Recommenders paper, which is a very famous paper, which takes the success of LLMs and applies to more ranking and retrieval use cases. More recently, Netflix also released some information about a foundation model they built for personalized access. And we also released a model which is a foundation model for recommendations, which only uses text, no other features. These are all examples where LLMs or transformers in general can be used for the Rexis pipelines. And on the right side is more traditional use cases of LLMs, which are more generative in nature. For instance, the hiring agent that I discussed with you, where we use LLMs as part of agentic workflows to improve the whole hiring pipeline for recruiters. And another example is Klarna's AI assistant, where they use AI assistants to automate a lot of the customer care, customer support problems for a lot of the ticket workload that they have. So these two bifurcated, this represents the bifurcation where you want to solve two very different set of problems, but it just so happens that both of these set of problems can be solved using LLMs or very similar technology at this point. So to summarize, what is the need for SLMs? So we kind of talked about LLMs have demonstrated remarkable performance across a wide variety of applications for search, recommendations, Gen AI. And from scaling laws, we know that larger models do have higher quality. Now, to deploy them, it takes substantial computational requirements. For instance, it's very hard to deploy a 100 billion parameter model for a use case which requires latency of less than 100 milliseconds. So what we are focused on at LinkedIn is how to build small language models that deliver high performance and efficiency in deployment. So that's been the main focus of this team and a lot of other teams at LinkedIn. Okay, so now let's dive into some specific details of LLMs used for ranking systems. Give me just 1 second. Sorry about that. For ranking systems, LLMs are actively being used for ranking, where they're being used for generating embeddings. This is something that's been done for a while. They're being used to generate interpretable reasons, to have recommendations, explainability. They're being used in modern search and QA systems to generate responses to queries. And I already mentioned agentic search is a big use case for LLMs. And they're also being used for other tasks. Now, each of these tasks, help improve results for essentially surfacing the most important results to a user, whether it's on a feed or for a search use case. Now, in subsequent slides, we focus on producing efficient LLMs, which are faster, smaller, and have lower cost of serving, especially for online sensitive, latency sensitive use cases. And a disclaimer that a lot of the techniques discussed in this presentation, it doesn't necessarily mean that we have implemented them or built them at LinkedIn. We are trying to provide a holistic overview of things that happen across the industry, and we don't endorse or recommend any specific method. So this is a slide from the Generative Recommenders paper from Meta, where going from the DLRM, which is deep learning recommendation models architecture on the left, the company has moved towards a more causal model, which takes inspiration from LLMs. From LLMs, we know that when trained on text, larger models trained on more data tend to lower validation loss, which tends to translate to better performance on downstream tasks, whether it's summarization, question answering, etc. Similarly, what Meta has found is that if you represent your data in a certain way and use a causal transformer, then you are able to demonstrate scaling loss, that the validation loss for your validation set or the AUC for your validation and test set also goes up with more training flops. So this is something that was not proved before, and this is a more recent development. And this is very exciting because now you have the ability to scale your recommendation models and expect to get more ROI out of those models. Similarly, we recently worked on another paper called LeeGR, which is inspired from Meta, where we also use a similar architecture for some recommendation tasks. And this is also inspired from an LLM paradigm, where given your activity on a certain surface, we take the history of that activity, we take all the actions you take on that surface, and we use a transformer to then predict the action that you will take next. And when we scale this training to more training flops, when we make the model bigger, we see a consistent increase in validation AUC across the board. So this is something that's being adopted not just by Meta and LinkedIn, but by several other companies as well around the world. And I think in the next 1 or 2 years, we'll expect more and more companies to move towards this architecture. Now, one big problem here is that these models can become fairly big very quickly. Serving them online is a challenge. So that's another area of research where how do you surface recommendations to users for use cases where the latency has to be less than 100 milliseconds or something similar. That's a very exciting area of research, which a lot of other companies are also investing in. So that was the intro. Now I'll pass it on to Yun. She will talk about efficient algorithms, specifically distillation.
Thanks so much. So yeah, I think right now maybe we can first dive into efficiency from the algorithm side. Like, how do you actually produce an LLM that is more efficient in training, easier to be served, while retaining a good performance or say quality. So we'll first look into like efficient LLM algorithms, which are like some alternative LLM architectures. I mean, the softmax attention is Well, it is a staple in transformer architecture, but it comes with a quadratic computation and memory complexity with respect to your sequence length. And this is actually posing a very significant challenge for processing very long context. While efforts on efficient kernel redesign, such as flash attention, kind of mitigates this bottleneck, this is not yet completely addressed. So to tackle this, a new family of linear attention has emerged as a compelling alternative, reducing the complexity to be instead linear with respect to your sequence length. And this approximation becomes very advantageous when your sequence length is far exceeding your model's hidden dimension, which is a very common scenario in some recent advancements that require long context, such as agents and reasoning models. And additionally, state-space models also offer a very novel framework for sequence modeling with some similar efficiency goal. And lastly, native sparse attention, published by DeepSeek team, also leverages hierarchical sparsity with some hardware-aligned optimization to achieve substantial speedups over the long context. And next, we shift our focus to efficient optimizers. And why we want to talk about this? Because training LLMs demand not only a very massive, large data sets, but optimization strategies that kind of balance computational costs with conversion speed and resource utilization. Like we all know that AdamW is the de facto optimizer and it just always works great. There are actually a lot of more advanced optimizers that either achieve better conversion speed or in other words, requires less training steps. Or there are also optimizers that require much less GPU memory footprint than Adam, which takes 8 bytes per parameter element. So convergence efficient optimizers aim to minimize the number of training iterations required. And for example, Shampoo leverages the second order information to precondition your gradients, potentially accelerating the convergence. And schedule free, as its name suggests, eliminates the need for manual learning rate scheduling, such as cosine decay. And it also actually provides much better convergence rate. And there is another one called Muon, which actually originates from an X thread. And Muon is applying a Newton source iteration to the parameter update to to orthogonalize it. And this can ensure that the update matrices are isomorphic, and in this way prevent the weight from learning along just a few like dominant directions. And on the other hand, memory efficient optimizers are trying to address the hardware constraints for training large models. And for example, Lion is more memory efficient comparing to Adam because it only keeps track of the first order momentum term. And Adam Mini is trying to extrapolate the observed blockwise structure of the Bayesian of MLP, and it only assigns 1 second order momentum for each block of parameters comparing to each single element in the parameter. And in a similar spirit, B-Adam uses a block gradient descent to also achieve substantial memory reduction. And lastly, Galore is sharing a similar incentive as LoRa, as it also performs a low-rank projection, but instead on the gradient to reduce the size required for your optimizer states. And next, we will explore one of the most powerful tools for compressing large language models without compromising much quality or say performance, and it is knowledge distillation. So knowledge distillation refers to the process of transferring knowledge from a larger and more powerful teacher model to a smaller and more efficiently served student model. And in the context of LLM, knowledge distillation is critical because direct supervised fine-tuning on a smaller model, which is a little bit worse on the generalization ability side. This will often fail to fully capture and fully match the teacher's generalization abilities. And through the knowledge distillation, we guide the student to mimic the soft outputs of the teacher, which is the probability distribution over the vocabulary space of the teacher, thereby kind of internalizing the nuanced reasoning and capturing uncertainty, which is not super possible with training with hard labels alone. So formally, the loss function used in knowledge distillation often involves minimizing the divergence between the teacher distribution, which is also which is here denoted as P, with the student distribution, which is denoted by Q theta, parameterized by theta, over the vocabulary space. And it can be formulated into this equation. And it can be read as, like, firstly, you define how to draw, given a prompt, how to draw a response from the prompt. We'll talk about how to draw, what are the different methods for drawing a response later on. And you also define what is the divergence measure, or say divergence loss, to use. And well, most of the time people will just use KL divergence. What distillation does is, given this sampling method and also given this specified divergence loss, it tries to minimize the divergence loss between the teachers and the students' token probability distribution over the sampled response sequences. And so now let's talk a little bit more about the response sampling. In particular, there are three major methods. First one is called supervised distillation, which directly takes the grad truth training label as the response, which is like just the instruction tuning training data. And this is, of course, the most simple one. And what it does is really just to replace the original hard labels after one hot encoding with the teacher predicted soft probability. And this also means that when you're computing next token probability, you always condition on the grad truth golden response. And beyond that, sequence level distillation ignores the response in the grad truth and instead use the response autoregressively generated by the teacher LLM. This actually provides a better global coherence in the sense that it not only captures the next token probability prediction, but also let the student to try to mimic the teacher's actions at the sequence level, not only at the token level. And on-policy distillation is a latest one, and it instead draws a response from the student model currently being trained itself. So this is kind of very similar to how in reinforcement learning, you sample an episode with the current policy being trained in RL. So this is why this method is also named borrowing the term on policy in form reinforcement learning. And one nice property of it is it mitigates the exposure bias, or in other words, the train inference time distribution mismatch, where the student model generates its own partial outputs during inference instead of conditioning on the teacher or the grad truth data. And another benefit of it is it only tries to align the students like learning with its intrinsic capability without just bluntly trying to let the student to match the generation from something that might be beyond its generalization ability, either to be the grad truth or to be the teacher's generation. And we would also like to share a little bit of our practical learning of doing on-policy distillation. And so first of all, it's always good to try to start by doing a preliminary either SFT or supervised KD before doing the on-policy distillation round. And this is mainly for bootstrapping the student model with some basic instructional capabilities. Otherwise, if you just start the student model as a pre-trained model, then the initial training steps where the student model might generate extremely poor responses will be inefficient. And on the implementation side, it is very helpful to do it in a heterogeneous framework approach, where you use an inference engine such as SGLang, VLLM, or TensorRT LLM to host a copy of the student model for faster autoregressive response generation. And after each training step, or say after each model parameter update, you synchronize the updated model parameter back from the training instance back into the inference instance. And the teacher model will actually be recommended to be hosted with a training framework for the sake of having a better logic precision. Well, also with some micro batching and a gradient accumulation approach, like demonstrated in the diagram below, you can partially hide the very time-consuming operation of doing on-policy distillation like on policy autoregressive generation with by overlapping it with the local forward and backward passes. So we talked about response sampling, and if we go back to the formulation of distillation, we mostly covered like what are the possible PY, what are possible choices of PY, and the other dimension that to distinguish distillation methods is what divergence measure that you are going to use, which is the D here. So if we denote the student distribution as Q and the teacher distribution as P, then forward KL divergence forces Q to cover every mode of P, while reverse KL will try to let Q to concentrate on whichever mode or whichever major mass that gives it the smallest penalty and just ignore the others. And it can be very clearly seen from the diagram below, where the red dotted line is the forward KL, and the green dotted line is the result from reverse KL, and the black line is the teacher distribution. So both forward and reverse KL can be unbounded, and there is a nice well-known one which is bounded, and it's called generalized Jensen-Shannon divergence. And all it does is to interpolate between forward and reverse KL using a bounded coefficient beta ranging from 0 to 1. And finally, there is also a very straightforward one called total variation distance, which simply models the absolute difference, or say absolute distance, between the two distribution curves. So far, we've been always talking about distillation from a bigger language model to a smaller language model on the next token probability space. And we will also like to just lightly touch a bit on something beyond that. For example, there is one technique called cross-context distillation, where the teacher and student model might be originally the same one, comparing to like the traditional distillation where you instantiate the student as something smaller, much smaller than the teacher. In cross-context distillation, what it actually instead does is to try to internalize the long chain of thoughts by distilling from a generation result, conditioning on a prefix with thought process and detailed prompt, into a generation conditioning on a shorter prompt and no thought. Also, like beyond token probability, there are also distillation on hidden states for sure, and more interestingly, attention score and the value relation, such as mini LLM, which is developed by Microsoft. And next, I will hand it back to Aman to talk a little bit about preference tuning.
Before we move forward, can we add one more panelist, please, to as a panelist? He's going to be a presenter. We can take a 1 minute break. Let me know when whenever I can get going again.
Can you hear me?
Yes.
What is the name of this attendant? Because we have two attendants here.
Yeah, I also don't see them. Maybe they haven't joined yet. That's okay. We can go forward. If they join again, I'll let you know.
Okay, because I need to because I use full screen, and in full screen I cannot do this. But if you want to go forward, we can do this.
Yeah, I think I'm just waiting for them to join. They said they joined, but for some reason they're not here. That's okay. We can keep going. They just joined. Yeah, Shao Tang. They just joined. Yes.
Okay.
Yeah, you can promote them to panelist. Amazing.
Okay.
Great. Yeah, we are all good. Thank you so much.
Please.
Cool. I'll get started for the next part. So this part is a pretty exciting area of research and also makes models useful. This is what I call the connector between GPT and ChatGPT. Essentially, how do you align a model to human intentions, values, style, preferences? And it has various different names. Some people call it preference tuning, some call it alignment. And the idea here is that you want to use a pre-trained model and align it so that it's useful, less toxic, produces more relevant answers. More recently, one particular method for post-training, which is like essentially, reasoning, has become really popular with DeepSeek. But even before DeepSeek, doing alignment training was really, really popular. So post-training refers to anything that is not pre-training, essentially, and preference tuning is one phase of post-training. Now, why is this useful? Because if you preference tune a model, you can significantly enhance the model quality, even along at least certain dimensions. So on the right side, we're showing Chatbot Arena leaderboard, where using a high quality human preference data, you can have a very small model compete with much bigger models, at least in terms of being faithful to certain questions in the prompt, being able to follow instructions. And this allows you to make smaller models kind of punch above their weight. Now, specifically, how does this happen? You take a pre-trained model and you fine tune that model on some data, and then you finally do the preference tuning. Now, to get into the entire detail is going to take an entire tutorial of this kind, but I will probably only talk about a very high level detail. So when preference tuning was first published by OpenAI in 2022, they talked about using this technique called RLHF, which is reinforcement learning with human feedback, where you use a reward model. And what the reward model does is it allows you to assign a scalar score to a prompt X and a response Y. And you use this formulation called the Bradley-Terry formulation, where the probability of a response Y1 being more preferred than a response Y2 given X can be expressed in this manner. And this allows you to collect a lot of data where for a given prompt X, you have a preferred response and a dispreferred response and a corresponding reward model. And some of you who use ChatGPT may have seen sometimes that even during ChatGPT sessions, OpenAI asks you to choose between two different variants for the A/B testing. And presumably this is how they also collect some of this preference data. And once you have this data, you can train a model on this negative log likelihood loss, where you're taking an expectation over a triplet. And the triplet is your input prompt X and your output YW, which is a winning response and a losing response. Let's take maybe certain examples. Let's say the X input is how do I, exercise to lose weight, and YW is maybe something which suggests something useful, and YL is something that suggests something dangerous. Then you want YL to be the losing response and not be preferred by the model. So this is just one example, and preference tuning requires a lot of data curation and creation. And this framework can be used then to align a model to generate desirable outputs. Now, the data is one part of it, which is probably, I would say, the most important part. But the second most important part is what algorithm you use. So at the top is the reinforcement learning with human feedback objective, where you use maximize the expectation of a reward model, followed by the fact that you don't want your policy pi theta that you're learning to drift too far away from some reference policy. Now, later, when other methods were developed, like DPO, which is direct preference optimization, people got rid of the reward modeling stage altogether, and they're able to implicitly mention the reward as, give me one second. So it allows you to parameterize the reward as beta times log pi theta by pi ref, which is a ratio of the policy that you're learning and a policy that you're trying to not move too far away from. Now, DPO is very popular. It's idiot-proof. Anybody can run it. It's something that everybody should try using because all it requires is one training run. And after that, several variants have come up, like Simpo and AlphaPo. AlphaPo is something we developed at LinkedIn, which are different flavors of DPO, which allow you to look at training dynamics and understand how to do optimization in a better manner. At the bottom is GRPO, which is more aligned with reasoning. It became very popular with DeepSeek, and Gregory will be talking about reasoning in a second. But these are all algorithms which are kind of similar, but give varying degrees of success. Now, in terms of the data, more recently, on-policy data has become really popular. Now, what is on-policy data? As you're training the model for preference tuning, instead of relying on data generated offline, you can generate samples from the current model and use some kind of LLM as a judge to select which is the preferred response, which is this preferred response. As you already mentioned during distillation, on-policy distillation works really well. And no surprise, on-policy training with this kind of method also works really well. And this is easier to scale up because all you are doing is allowing your model to generate more data, and your judge or oracle is something that needs to be very powerful. Off-policy data is also super popular. This requires you to generate data via humans or another model offline before you do any training. And this is resource intensive because you either need human in the loop or you need another LLM to produce high quality data. So one very solid data set is MACPI, which is generated using Llama 405B. And Ultra Feedback is another popular data set used in several different papers. Now, some of these methods, like DPO, are called direct alignment algorithms. They actually lead to some kind of issues in training. So one issue in training is you typically want the margin between preferred and dispreferred responses to widen. And sometimes when you optimize using DPO, you can excessively lower the probability of both the preferred and dispreferred response. So here's an illustration from a famous paper called likelihood displacement, where for a preferred response y plus and a dispreferred response y minus, we see that both their likelihoods go down with time. Y minus goes down more, but even y plus starts going down a lot. And that can lead to some random response like Z bubbling up to the top, conditioned on X. So conditioned on X, you may start seeing other responses showing up. And this is known as catastrophic likelihood displacement. So this is something that has to be controlled very carefully. And our paper, AlphaPo, actually talks a lot in detail about this. So feel free to check out that paper. Here is other examples from other papers where with DPO and other methods, you see that the likelihood of different responses goes down with time, especially if you tune hyperparameters, and that can lead to issues in training. So just to summarize, what are the practical lessons of applying preference tuning? Data is everything. You want your data to be as high quality as possible. On-policy data trumps everything else, just like distillation. Even in preference tuning, on-policy data is everything. And here are some specific algorithm tips. If you're using methods like Simpo, then you need to tune hyperparameters. That's very, very important. These methods are sensitive. You need to tune them. But once you tune them, they work really well. And if Simpo doesn't give you the best result, then AlphaPo can take the Simpo configuration that you have, and with a small positive alpha can boost things a lot better. There are other methods like SPPO, which is self-play preference optimization, where you can apply SPPO and Simpo in conjunction to improve your model even further. So once you have the right data set up, then you can play with algorithms and in order to get you the best final performance. So this was about preference tuning, where we're trying to make smaller models be more faithful to instructions and kind of punch above their weight. More recently, reasoning has become very popular, and Gregory is going to talk about how to do efficient reasoning.
Thanks. I'm Gregory, and I'll just briefly go over some important and relevant approaches for length-controlled reasoning. So just to give the fundamentals, earlier LLMs typically had a prompt, and then it would output a response that directly answers the initial questions. However, in more recent times, starting from important examples like the ChatGPT O1 model or DeepSeek R1. Newer approaches have been used where the model will not only output its final answer, but try to output its reasoning along the way as well. This is beneficial since it allows for scaling of computation at test time, leading to more accurate answers. On the right is an example of what this could look like, where if you have a math word problem, instead of going directly to the final answer and potentially getting it wrong, chain of thought reasoning, the model outputs its intermediate calculations, and then due to its autoregressive decoding can leverage those intermediate steps while going to the final answer. This chain of thought reasoning can be enabled in trained LLM models through a variety of methods like different prompting strategies, supervised fine-tuning, or even RL-based training approaches. There's a lot of work in how to leverage what is called test time compute, so increase computation like this for better performance rather than scaling the training data or model size. And different strategies like sequential or parallel scaling can affect it. For now, we'll focus on sequential scaling due to its superior performance in the context of length-controlled reasoning. So since this tutorial is about efficient use of LLMs, it's important to understand how the budget of those reasoning traces affect performance. So while long reasoning chains can result in higher accuracy, it also requires a lot of computation to output all those tokens on the way to the solution. So to define the problem directly, let's let our efficiency metric be the number of tokens used for the test time compute reasoning. Then let's explore two recent relative methods for controlling this trade-off between accuracy and computation. The S1, which is a simple prompting truncation approach, and L1, which is a more sophisticated RL-based training approach. So the S1 paper takes a simple methodology to show test time scaling in chain of thought reasoning. What they do is they start with an instruction following, but not chain of thought reasoning model. And by carefully selecting some examples of chain of thought reasoning traces, they can enable chain of thought reasoning within their model. Once they have a chain of thought reasoning model, for our purposes, the interesting part is that by simply appending weight at the end of the model output, they can make the model continue to reason longer. And then by forcing the model to reason longer, this gets it to have more accurate outputs. On the other hand, if they want a lower amount of computation at inference time, they can just put an end of reasoning delimiter and force the model to end its thinking. Despite the simplicity of this approach, it is able to show test time scaling between computation and accuracy, which was the main goal of this paper. Building off of this idea of length-controlled reasoning, the L1 paper instead tries to modify the training of an already chain of thought reasoning enabled model in order to carefully control this trade-off through a prompting and training strategy. So in order to feed back to the model, it is given a reward signal for correctness of the output in response to some prompts, as well as whether it satisfies some length constraint. They explore two different ones, L1 max, which just penalizes the model for going above the specified reasoning length, and L1 exact, which penalizes the model for going either above or below the reasoning. We see on the graph to the right that taking this approach to controlling the reasoning length leads to a much better efficiency curve between tokens used and the pass rate, where it shows that compared to long reasoning models, you can maintain much of their performance while reducing the tokens used, which essentially it ends up forcing the model to stop using gap words or filler words like secondly, next, we are saying, things like that. An interesting conclusion of their paper is that it actually requires a relatively low amount of computation or fine-tuning with this reinforcement learning approach to change a long length reasoning model to a more efficient one. Right? Now, Aman will discuss training efficiency.
Before we move forward, can everybody see the slides? Just want to confirm that you can still see the slides. If you can give me a thumbs up. Okay, you can see the slides. Awesome. So next, Shao will talk about training efficiency. Shao, do you prefer to share your screen?
Yeah, everyone can hear me, right? I'm going to share my screen. Yeah,
Go for it.
let me share my screen. Yeah, so can everyone see my screen?
Yes.
See the slides?
Yes.
Okay. So I'm going to talk about the training efficiency as we have covered some basics intro. So the first about the training efficiency is like to understand the bottleneck where we have like peak memory usage. It includes like model parameters, gradients, optimizer states, activations, inputs, and other temporary tensors, and some communication buffers. And for the also there's a bottleneck on the computation efficiency that's measured by throughput, model flops utilizations, and communication overhead where internode is usually fast, while internode, the communication is slow. So scaling training requires trade-offs. So furthermore, we're trying to understand this by the very famous roofline models, where we understand the trade-off between memory versus compute bound. So on the slide, there's a toy example where the y-axis is attainable flops per second. The x-axis is arithmetic intensity, so flops per byte of the data. So when we have very low arithmetic intensity, then we are considered it's at memory bounded, because for each flops we only do for each byte of data we only do very small flops of computation. And as we increase the arithmetic intensity, it becomes compute bounded, because for every byte we're actually doing much more computational flops. So, and the orange line is a slope, which is like is basically indicating the peak bandwidth, which is bytes per second. And it's interesting to notice that usually the peak hardware flops per second is different by different like data types. That's why we often heard that when we switch to lower position, we get like higher hardware flops. Yeah. So the next slide, let's start the understanding from the single GPU standpoint. So the naive training flow, as from the summarization from the Hugging Face website. So the first row, like the purple one, is basically the sequential, like the forward pass. And then in the end, you will get the model output. And in the reverse order, you get the backward, like in the orange arrow, and then you compute the gradients, and then you do optimizer update step. So this is the naive training flow. And the first is we can leverage in the so-called gradient checkpointing, where certain amount of the computation can be redo, like certain quantity can be recomputed during the backward instead of always cached in the system. So the flow, like forward pass, is the same, but in the backward, we would do a small forward step, then compute the gradient, and the remaining the same. So there are two different flavors. The first one is the full gradient checkpointing, where most of the activations are discarded after forward computation and recompute during the backward pass. So this case, we can save a lot of memory, but as you can imagine, right, like we are recompute most of the stuff, so it would cause a lot of the training speed slow down. And for the selective, so only specific intermediate activations, typically those with like largest memory footprint and lowest cost in compute, are discarded and recomputed. So using selective gradient checkpointing results in a better trade-off. And for the next technology is a gradient accumulation, where we are not able to fit a large enough batch in the GPU node that we like, right? So the idea is like we can do small batch forward, backward multiple times and then accumulate their gradients. So this is how, as it illustrated, right? Here is like we do 3 forward, 3 backward, and then we do 3 gradients, but we accumulate that so that to simulate actually effectively we are doing 3 times larger of the batch. But actually in the memory, you always only have 1 single batch. And then the remaining flow is the same. So in this case, we can actually try to mimic the training with large batch size, but actually we only have a small batch in the memory, in the training flow. And then we accumulate their gradients. And we have talked quite a bit on the single GPU training, and that's most of the techniques we have covered. Now we are going to dive into the multiple GPUs, like multiple nodes. So it's very important to cover the parallelism. So we are going to talk about a various of parallelisms and mostly focus on like the simple one, like data parallelism, and which comes first. And then we will talk about the pipeline parallelism and tensor parallelism. And there's also like context parallelism and expert parallelism for MOE. Yeah. So for the distributed data parallelism, the idea is quite simple actually. So in the first row, we have 3 layers. So first, so forward, right, 0, 1, 2 layers, and then backward in the reverse order. Then we have to do all reduce for the gradient. And then that's the GPU communication as indicated by the purple box. And then, so this actually slows down the training quite a bit because you have a communication time where no computation is happening. So the one improvement is we can actually try to make the communication overlap with the computation by chunk the all reduce into small chunks, right? And then so immediately after the forward, we can start to all reduce the chunks of the all reduce gradient for the second layer. And that's one way, but this usually, like if we only always do a small chunk communication, it's actually not efficient. So we can actually, batch them up, make the overhead is smaller. So we see the last row is basically immediately after forward, like after the second layer of the gradient is computed, it will get communicated like to all reduce, while the computation for the first layer of gradient is still happening. So this like overlaps and also reduce the overhead for the communication. Next, we have the zero redundancy optimizer and the FSDP implementation. So the distributed data parallelism, the input batch is sharded, everything else is fully replicated across different GPUs, and gradients during the backward parts are all reduced. And then for the zero and the FSDP, we remove the redundancy replicating in model parameters, optimizer state, and synchronized gradients. So basically, the model parameters, optimizer states, and the gradients are sharded. And this is the typical flow. So notice that initially we will load model shard, and then when we actually doing computation for the forward pass, we still need all gather for all the shards to complete the computation. And similarly, we need an all gather for the backward pass. And then immediately after backward, it's a reduced scatter for the gradient. So this is a typical flow. So you can see that we still need like all gathers in forward pass as well as in the backward pass. And for the tensor parallelism, like activations are sharded along the hidden dimension, weights are sharded along the feed forward dimension. Activations and are then gathered before up projection. The results are reduced scattered after down projection. And for the pipeline parallelism, the activation from GPU, like one GPUs will be sent to the next GPU. So the pipeline paradigm is like you distribute the different layers to different GPUs. Yeah. And then the tensor paradigm is like block matrix computation across different GPUs. So given some examples, for the tensor paradigm, like we have column-wise on the left, which indicates it's like a block-wise matrix computation. And for the row-wise, we need to basically split the two matrix independently, and then it will be immediately clear when this is useful. Yeah. So for the tensor paradigm, there's obviously some advantage, right? It's capable of training extremely large model that can fit on one GPU. And when applied with data paradigm, it's reduce the ring size of collective or reduce altogether, avoiding being bounded by ring latency when the number of GPUs grows large. But of course, as we mentioned previously, the downside is like we have to synchronize, like downstream operations are blocked by this synchronization. Yeah, and on the right hand side, this is the illustration for the MLP and self-attention. Yeah, and then we can go to the pipeline parallelism, and basically the idea is we distribute the layers into different GPUs. So as an example, let's consider we have 16 layers distributed across 4 GPUs, right? Like this is the first row is like naive sequential computation. We compute through like 1, 2, 3, 4 layers, then go sequentially. And then after we compute the 16th layer, then we do in the reverse order of the backward, right? So we can see the gray area, which is divide idle, which is basically like a bubble. So it has a large bubble. So the immediate improvement is like instead of a single large batch, we can split batch into smaller like micro batch. And then in this illustration, it's actually we are using 8 micro batches in the example on the left. And then this pattern is called all forward and all backward. So basically, we are computing batch over batch, and we can see the bubble is actually smaller than compared to the first one. And we can also have, yeah, one thing to notice, the reason we call it all forward, all backward is like we are computation the backward only after all the micro batches forward has been completed. And then the next one is we can have one forward and backward. So basically, we first compute the first micro batch. Immediately after its computation, we can start to compute the backward for the very first micro batch. So this reduces the bubble even further. And then the last one is actually we have interleaved stages. So here is like instead of like naive scattering of the layers across different GPUs, we can have a more smart way of distributing layers across GPUs. So like in this case, we have both like first layers and last layers both on GPU 1. So it's like it will run in circle so that the further the bubble can be further reduced. So after we cover the training paradigm, we are going to move into the training precision, which is another very important aspect. So normally a number like here as an example is 32 bits. It's represented by like a sign bit and some exponent bit and some mantissa bit, right? And the exponent bit is really controls the range of the number, and mantissa bit determines the significant figures of the number, like basically the precision. And then in this table, we can see, okay, when you lower the total bits, you get basically lower of the range, like the exponent, and as well as the mantissa, like the precision, right? And here is a great illustration. In the top panel, we can see the range, right? Actually, if we see compared to the float 32, the B float 16 has the exact same dynamic range, while others has much less range. But on the other hand, when we talk about float point resolutions, basically here we're trying to see, okay, what's the minimum number that's representable in the interval of 1 and 2, right? And then the minimal here is 1 plus 10e minus 4. And as a note, for the FP32, the minimal representable number is 1.19 multiplied by 10e minus 7, that incremental. So it definitely hits like 10 to the minus 4, right? But for example, the float 16, if you see the red bar here, the minimum representable number after above 1 is like 10e minus 10 to the minus 3. And then for the B float 16, although the dynamic range is larger, its resolution is actually lower. So basically it's like the minimum is like 10 to the minus 2. And it will be, the resolution will be even lower for float 8 number. So basically there's a bunch of number that it's not representable while you are using lower precision numbers. And here is a summary. So basically, as we lower the precision, usually we get like lower numerical precision and lower numerical stability. And of course, we reduce the computational operation so that we get like, we can train things faster because we can significantly reduce the number of operations needed for training. And that's why it's proposed that we can use like mixed precision to achieve, whenever there's high precision needed, we still use FP32, but in some of the intermediate step, we can actually use a lower precision. So the recipe is like, we use FP32 master weights and optimizer states. So higher precision always for accumulated values, but lower precision in the intermediate results. And then we need a low scaling for FP16. So here is a typical like torch flow. On the left is like a typical flow when you have like FP16, where you need a, low scaling right in the middle. And it's actually important to know that if we want to perform any type of operation on the gradient, we first need to actually unscale it. So let's say here we use like the gradient, like clip grad norm. So we first need to unscale, and then we apply the clip grad norm, and then do the optimizer like step and update. So the last is like there's recently there's an emergent interesting in the FP8. Mixed precision, and then it involves like dynamic quantization versus static quantization. And then the quantization is, there's a abundance of different strategies, and at different granularity level, as we show in the bottom. So basically like per tensor, per group, per embedding, right? Basically, without appropriate quantization, the training will not be stable. That's why there's a lot of work or effort on that quantization front. And as we have covered like single GPU training, multiple GPU, and the mixed precision, those are like at high level, right? This is something that once we apply, if we still need additional like improvement, then we can dig into very low level, like kernel effort. So first is, why do we want to use kernels, right? There are many advantages. First, like we can reduce overhead, and significantly we can fuse multiple operations into one, like as we wish. And we can also maximize the parallel throughput, like hide memory latency with concurrency, and then we can optimize the memory access. So as defined by our kernel, right? And then we can enable a lot of algorithmic tricks, because we have really great control on every operations. And some of the common techniques, including like tiling, reuse data on chip, basically optimize the usage of shared memory instead of like global memory. And we can also do like recomputation, like recompute intermediates rather than store them. And this basically by a lot of benchmark. And then we can do like loop unrolling and fusion. And then we can have a lot of, we can have two main frameworks, which is CUDA and Triton. And CUDA is more low-level control. And for Triton, it's like Python native. And then there will be a lot of optimization covered like automatically, but you lose a like lower granular level controls. And here is some like very high-level comparison. Like on the left, we have like Liger, it's Triton kernel, but it's still native in Python. And on the left is a CUDA softmax kernel from DeepSeek's repo. So as you can see, the code for the CUDA kernel is significantly more complicated, right? Like even for this, if you see line 167 for the exponential to like f, right? You have to actually write a particular like exponentiate function in order to fully, make this powerful. So there's a lot of small tweaks when we go down to the CUDA path. Yeah. Now I have finished the training part. I will hand over Aman to continue the inference part.
Thank you, Shao. So I think we are at break time, so we can continue the rest of the presentation after the break. Just a question for the organizers. Should we stay on the call for the rest of through the break? We can do that.
Any questions? No?
Yeah, we're also happy to take questions if you have any.
Okay. So please don't leave the recording, the session.
Sure.
Yeah.
Sounds good. We'll just stay on mute and we'll reconvene in about 28 minutes.
Yeah.
Thank you. I will leave the tutorial website up. So if anybody wants to look at the website, feel free. Let me go to that slide. We'll get started in about 7 to 8 minutes. So we'll get started with the second half of the tutorial now. Let me move to the second half slides. In the second half, we'll be talking mostly about inference optimization. So I'll pass it on to QQ, who will talk about inference.
So thanks, Emma, for the introduction. So this is Qing Quan. So you can call me QQ. So as we are transitioning to the second half of today's session, we'll now focus on another critical aspect, which is efficient inference for large language models in generative and predictive recommender systems. So while training often attracts the most attention, but in practice, inference dominates operational costs and user experiences. So training happens once, but inference happens millions or even trillions of times across user requests. So our objective in this next session is to explore strategies to make inference faster, cheaper, and more reliable, while still maintaining the high quality and accuracy of LLM to match users' expectations. So first, let's build a shared mental model about what affects inference speed. So LLM inference can be broken into three broader stages. So the first one is instance provisioning, where we're spinning up resources, containers, and models. And the second one is the platform and network overhead, where we do the routing on the request and also receive the responses. So the third one is the model execution itself, where we actually do the token generations. So each step introduces delays, and inference latency can be measured by the metrics like time to first token, which is TTFT, and time per output token, which is TPOT. So throughout this talk, we'll learn how to optimize each of these. So when deploying in real-world systems, like recommender system engines, chatbot, copilot, so measuring the inference speed requires a special attention. So some key performance indicators include some client-side latencies, which is user-perceived delay, and also service latencies, which is model-side processing time, and also the throughput, which is token per second, or we call request per second. So beyond just averaging the performance, so the percentile metrics like P90 or P95 latencies also pretty vital, because in online services, the worst case delays often defines the user experiences. So the ultimate goal is to increase throughput over fixed hardware or resource capacity, subject to the service level objectives, SLOs, on these measures, which we term those satisfied requests as goodput. So now that we have some fundamental metrics that we care about, let's dive deep into how to optimize them. So before we can improve inference, we first need to understand and measure where time and resource are spent. So this needs a thorough benchmarking and profiling. So, so the goal of the benchmarking is twofold. The first one is the resource estimation and allocations, where we try to understand how much compute, memory, and network are needed. And the second one is about performance optimization, where we try to identify the bottleneck and opportunities for acceleration. So several key metrics are critical when benchmarking LLM inference pipelines. So the first one is the start time measurement. So this covers the instance provisioning phase, like how long it takes to allocate resources, boot machines, download containers, deserialize models, and start containers. So optimizing this stage is crucial for reducing the cold start of container. And the second one is the platform time. So this is time spent purely on the network and routing the request through the service infrastructure. So even if the model is fast, full platform routings can also introduce unacceptable delays. So the third one is LLM time. So this is the heart of the inference performance, where we measure by the time to first token and time per output token, and also some client side visible latency and throughput metrics. So importantly, we often benchmark not just the average, but also the P90 and P95 latencies, which capture the real-world user experience. So the first one is the recycle time. So after serving a request, the infrastructure needs to clean up, like recycle the containers, reclaiming the memories, and detect potential garbage or stale nodes. So the efficient recycle time management auto ensures the resources can quickly serve the next wave of incoming requests without idle delays. So overall, a well-designed benchmarking process gives us a holistic view from hardware to application level metrics and enable the truly effective inference optimization. So the focus of LLM inference profiling is different than training profiling, because during the inference profiling, it's important for us to focus on some, not just the GPU utilizations, but also some KV cache behavior, a prefill versus decode time speed, and also like only with those concise, precise profiling can help us make some smart, cost-effective optimization decisions. So tools like PyTorch Profiler, TensorBoard, NVIDIA Insight System, and Insight Compute, and some customized benchmark tools for real-world token-by-token inference are quite essential here. So for example, the Insight System can give us a broader overview of the entire CPU and GPU streams, where you can see from the figure that you can also have some collective results for the kernel utilizations, and also how much time is spending on each stream. So similar is for the PyTorch profiler, where we give an example here that when we benchmark the SGLang for some speculative decoding experiments, we have some extra additional costs spending on the slicing the tensors. So through the profiling, we can like see that to reduce those like redundancies. And also like if you want to have an in-depth understanding of each kernel performance, some cycles and stale times, you probably need Insight Compute in order to understand. So we provide two links for here. One is from the GPU mode tutorial, another is SGLang profiling guide, where you can refer to and understand each of them. So inference engine are responsible for like orchestrating the entire flow from user input to model output efficiently. So they ensure efficient model execution by optimizing token generation. So managing the KV cache reuse, and also it helps to reducing the redundant computations and the streamlining GPU utilizations. So beyond just executing models, these engines also handles critical aspects like resource management and optimizations, such as dynamic batching of the request, memory-aware scheduling, and also load balancing across nodes. So these also facilitate pipeline integration, providing some hooks and APIs to connect with upstream applications like chatbots, search engines, recommender systems, and also some downstream infrastructures like storage and logging services. So many inference engines offers advanced features, include speculative coding, attention sparsity exploitations, efficient streamings of tokens, and also support some heterogeneous hardware setups. So popular open source frameworks leading these innovations include VLM, SGLang, TensorRT, TGI, and mdeploy, and also DeepSpeed, MII, also called FastGen. So in short, choosing and tuning the right inference engine is pivotal and to help achieve production grade performance, and also help to make it cost efficient. So especially when we serve much larger models. So let's move to the first practical bottleneck, which is a model loading. So one of the major hidden bottleneck in deploying large language models is model loading time. So these models can easily reach like hundreds of gigabytes in size. For instance, the recently released DeepSeek R1 model. So even with FP8 compression, so this 671 billion parameters can still require like over 30 minutes to load for the first time, even on a high performance NFS system. So while Linux page cache can significantly accelerate the subsequent load, but this initial model load and recompilations and optimizations with like CUDA graph capture, torch compile remains like pretty painful and time consuming. So thus, like optimizing the model loading is essential for production systems, especially to reduce cold start times and to enable scalable auto-scaling during demand spike. So several key strategies are used to accelerate the model loading. So the first one is the container size optimizations, where you can use smaller container images, trimming some unnecessary Python dependencies, and also separating the CUDA runtime layers allowing you for much faster container pooling and initializations. Some other techniques like cast the container in pods, model storage optimizations, and also like the network file system NFS also allow you to mount the same model quickly and load the disk caches in the Linux page cache to help you absorb high read bandwidth demand. And also some recent techniques like CPU RAM FS, which can speed up the downloading and the uploading, which where they store the data in the RAM file system instead of disk. So as shown in the figure adopted by Anyscale benchmarks, so this technique can collectively allow models that once took like tens of minutes to load to be available in just seconds or even a few minutes. So this can unlock fast elastic scaling of the AI services. So as we move deeper to optimizing LLM inference, we need to address a critical challenge, which is routing and scheduling. In production systems, serving LLM is not just about how fast a model can generate tokens. It's also about how efficient we can manage thousands of concurrent user requests, all differing in like complexity, length, and also urgency. So routing determines where to send each incoming request, to which cluster, node, or even which specific model instance. So smart routing can minimize the network hoops, reduce the latencies, and also balance the workload effectively. So scheduling, on the other hand, happens after routing, which decides how to batch, prioritize, and also execute those requests. So good scheduling can maximize the GPU utilizations without letting any single request starve. So together, routing and scheduling forms an invisible control plane that powers scalable, responsible LLM service at a global scale. So at its core, scheduling LLM inference is a balance act between latency and throughput. So if we wait too long to batch requests together, latency will grow and users experience some sluggish responses. So if we serve too aggressively without batching, we kind of underutilize the GPUs and also increase the operational cost. So traditional batching scheduler are kind of static, but modern LLM serving demands like dynamic schedulers that can adjust in real time. So those dynamic schedulers can group those similar queries prompts together to minimize the padding waste and reuse the prefix cache. It can dynamically merge and split those micro batches on concurrent queue states, and also like using some early profiling results of the prompts to dynamically predict the optimal execution patterns. So let's zoom into a typical real-world scenario. So in some high-traffic production systems where queries per second, the QPS can spike into hundreds or even thousands. So we inevitably end up with a backlog of queries waiting to be served. So we can model this situation as a queue, which is a collection of the Xi and Ti, where Xi represents the query prompt, and Ti represents the arriving time of this query. So given this queue, so a natural question arises, which is how do we determine the processing order of those prompts? So there are two baseline strategies. One is called first come, first serve, which we process requests strictly in the order of arrival without considering any similarity between them. And it is simple and fair, but doesn't optimize for opportunities like prefix caching or reuse, where like multiple prompts can share the common prefixes. So the second baseline is called longest prefix matching, where we prioritize the queries with most prefix reuse. But in this case, by maximizing the prefix reuse, we reduce the redundant computation and lower the average processing per query. So as studied in some research papers, it shows that the LPM, the longest prefix match, can significantly outperform FCFS in terms of both latency and throughput, especially under some bursty high QPS conditions. So modern LLM serving frameworks increasingly incorporate prefix-aware scheduling mechanism in order to optimize the system performance. So although the LPM helps significantly improve throughput by maximizing prefix reuse in real-world overloading online settings, so when the system faces high QPS and also have some deep query backlogs, so we must kind of balance both goals. One is the high average throughput to reduce a growing queue backlog. Another is to still keep the low latency, the P95 and P90 latency, to maintain the acceptable user experience even under this load. So the LPM alone in this case, while excellent for maximizing the shared computation, doesn't account for those arrival time of individual queries. So this can lead to unfairness, where the new request might be repeatedly deferred because they don't share enough prefixes with existing batches. So to address this, a more balanced approach has been proposed, by Gregory and our team. So which is called the key LPM algorithm. So this key LPM algorithms, for every scheduler cycles, we follow the key step of LPM, which we select the queries that maximize prefix reuse and throughput. And then we insert one step of FCFS, which allow the oldest waiting request to be processed, regardless of the prefix similarity. So this cycle then repeats continuously. And by periodically inserting FCFS step, so the key LPM ensures that no queues starves indefinitely, and while still benefiting from most of the throughput gains of LPM. So this results in high average throughput and also low tail latency and fairer service across the diverse query patterns. So, and the hybrid scheduling design embodies this kind of programmatic optimizations increasingly needed in the production ARM systems. So we are exploring the basics of scheduling and prefix reuse. Let's focus on another critical optimization, which is the prefill and decode disaggregation. So in high QPS environment, so one major challenge is how to effectively schedule prefill and decode affixes across shared infrastructure. So let's first look at the traditional scheduler approaches, which is the prefill first scheduling. So this prioritizes prefill batches over decode batches. And in this setting, decode tasks often get interrupted by large prefill jobs, resulting in a pretty poor P99 latency, especially on the P99 inter-token latencies, which means that the user experience irregular jumpy token generations. And another approach is mixed batch scheduling, which try to mix prefill and decode tokens within the same batch to optimize the GPU utilizations. However, prefill tasks usually take like much longer than the decode steps. So as a result, this decode are still delayed and leading to some bad inter-token latencies even within mixed batches. To address these problems, the idea is to do the PD disaggregation scheduling. And the idea here is instead of doing some mix and prioritize prefill or decoding with the same resource pool, we try to separate prefill and decode workloads on different nodes or clusters. So these architectural changes has a powerful impact. First, the decode-only nodes can focus entirely on the fast, responsive token generations. And the prefill-heavy nodes can handle larger, more compute-intensive prompt encoding without blocking those downstream inference. So the results is nearly ideal, nearly ideal inter-token latency. So because the decode operations are no longer interrupted by heavier prefill operations. So which you can see from the figure that if you even have some per GPU large request, you can still keep some pretty good output, which satisfy the SLA, the server side objective. And also like the PD disaggregation achieves much smoother and lower and more stable token generation latency curves compared to like traditional scheduling. So this is a great example where architectural disaggregation is not just algorithmic tuning leads to a major leap on the system performance. So Kiwi cache management is another critical component for speeding up IOM inferences. So the Kiwi cache stores the hidden states of the past tokens, which allows the model to avoid redundant computation during autoregressive generations. So how we organize and access this cache greatly impacts both memory efficiency and runtime latency. So page Kiwi cache is the commonly used designs. So when the page size is exactly 1, it means that each token is individually accessible in the memory, in the cache memory. While this can introduce more memory fragmentations. So although this introduces more like memory fragmentations, it kind of greatly simplifies the implementation of prefix caching. So since each prefix can be individually matched, copied, and reused at a token level granularity. So it is pretty suitable for the systems like dynamic prefix reuse is critical. For example, the retrieval augmented generation, RAG, or like multi-turn dialog applications. So when the page size is greater than 1, so the cache is organized in larger pages where each page contains multiple tokens. So the advantage here is like we can leverage the contiguous memory layouts so that the kernel can launch it faster. And the GPUs are more efficient when operating over continuous like chunks of memories which can also reduce the overhead from scattered memory accesses. So with these foundations, now let's zoom into the inference physics, the prefill and decode optimizations. So we know an LLM serving pipeline inference typically divided into two phases. So one is the prefill phase, where the model processes a full input prompt and builds up the KV cache for the first time. And the decode phase, where the models reuse the KV cache and generates output tokens autoregressively one by one. So during the decode, the KV cache enables us to avoid recomputations. Every new generation only depends on the last new tokens. However, during the prefill, there's no pre-existing caches to rely on. Suppose we don't have the previous cache in advance. So the model must process the entire input sequence from scratch and flowing through all the layers and all the past tokens. And as a result, the prefill is heavily bounded by computation, and it creates a latency void if you don't handle it properly, especially with long prompts or larger batches. So thus the goal of prefill optimization here is simply yet crucial, which is to reduce the time to first token as much as possible. And also we want to enable faster throughput across the full inference pipeline. So as we will see in the next set of slides, so there are multiple layers at which we can optimize for the prefill phase. So at the data level, model architecture level, engine schedule level, and also even the infrastructure design level. So continuing with the prefill optimization. So first layer we can target is the data level. So over the past few years, we've seen user prompts become increasingly longer, driven by the trends like in-context learning, chain of thoughts, reasoning, RAG, and multi-turn dialogue systems. It's now pretty common to see that the prompts can exceed like 20K tokens in enterprise use cases. So however, these longer prompts introduce a major challenges for the prefill, which is a high prefill latency because the model must process all the token sequences before the generation can start. So, and also the model has some limitations on the context windows, even for the models with larger maximum token limits. So it creates some heavy compute cost per request, and also like makes the performance degrade a bit. And also forgot some important information lost in the middle or of the massive prompts. So how to address this? So one powerful approach is the prompt compression. So as illustrated here, so the prompt compression techniques aim to retain the essential information and reduce the token count dramatically. And also try to maintain the, or even improve the downstream task performance. So the simplest way of doing this is just a rule-based method, but that requires some expertise and also hard to be generalized for different applications. So LLM Lingua is one important approach here. So which try to use a small LLMs to perform the information density aware prompt compression. It prioritizes critical tokens based on the entropy and semantics. And also the LLM Lingua 2, the second version, extended by adding cores to fine compression recovery, using some trend distillation from the larger teacher models like GPT-4. So some other important initiative is DSPy, which is a flexible framework that originally allows user to like programmatically optimize prompts for minimal length without sacrificing quality, but it can also be used here to reduce the prompt length to do the prompt compression. So fundamentally, these methods treat LLMs themselves as compressors. So models capable of understanding which part of the prompts matters most and rephrase or filtering accordingly. So by compressing prompts effectively, we can shorten the prefill time dramatically and also enable the larger batch sizes so that we can improve the overall throughput without retaining the model itself. So beyond data level optimizations, the model level strategies also plays a key role in speeding up the prefill phase. So we know that MLP and attention are the two key components in LLMs. And mixture of experts, the MOE is a common architecture selected to reduce the MLP bottleneck on latency and throughput. However, with the increasing of the prompt length, the core bottleneck in prefill usually lies in the attention mechanism. So to mitigate this, researchers have proposed introducing like sparsity into the attention computations, not only in decoding, but also during the prefill. So some papers try to discover the sparse pattern schemas from a small set of calibration data, without retraining the model from scratch. For example, in the M inference paper, it focuses on the 3 patterns. The lambda shape hat, which in this pattern is similar to the streaming LLM, where we keep where each token mainly attends to the triangular neighbor around itself, like a sliding window, and also attend to the tokens at the very beginning. So this reduces attention complexity significantly while still capturing some key local context during prefill. And also there are some vertical slash hat and also block sparsity hat. So the sparse attention helps lower the memory bandwidth pressure and also reduce the compute load, which are powerful complement to the prompt engineering and system level scheduling strategies we discussed above. So we want to point out that despite MLA absorb can reduce the latency during the decode stage, so the MLA for prefill stage can also help increasing the prefill throughput. So another thing that is worth mentioning here is that these architecture level optimizations usually needs to couple with the design implementation of the kernels in order to achieve the real speed up. So other crucial techniques for prefill optimizations are the model pruning and quantizations. So let me hand over it to Keihan, who will introduce how pruning and quantization approaches can make larger models not only lighter, but also significantly faster during the prefill stage.
Thank you, QQ. So yes, I will cover some of the slides related to model compression, namely pruning and quantization. I will start with pruning. So basically in pruning, the idea is that you want to remove some weights from the network. We want to set some weights to 0, basically. So this will help us to obtain a sparse model that hopefully it can help us to reduce the compute and memory requirements. There are different approaches for pruning. There is the or semi-structured pruning, unstructured. In unstructured pruning, basically you want the weights to be equal to 0. Look at the picture on the left over here that shows most of the weights. The white cells are equal to 0, for example, or the blue cells equal to 0, but there isn't any specific pattern on where this location of non-zeros are. On the other hand, we have the structured pruning or sparsity, where, for example, we want the rows of these matrices to be equal to 0. When we are doing unstructured pruning, we are pruning individual weights. Unfortunately, it is generally very difficult to accelerate matrix multiplication when we have unstructured sparsity. We really need some sort of specialized hardware or specialized kernels. However, because there isn't that much structure in the sparsity that we are considering, usually the models that are pruned under unstructured regime, they retain the quality of the original model a bit better. In contrast, when we have structured pruning, because we're pruning sub-components or some channels or some rows from these matrices, we obtain physically smaller models, which means that we can just speed up these models on any hardware. However, because we are enforcing some sort of constraint on the model architecture, this can lead to some accuracy loss after pruning. So the general approach that people use for pruning, one of the most standard ways is layer-wise pruning, which basically we prune each layer separately. So let us first introduce some notation. Here, let's say we have a linear layer. So let W denote the weights of this layer, and let X be the activation inputs to this layer. So the output of this layer will be W times X, and then the nonlinear activation. And let us assume that W hat are the weights after we prune the weights, so it's going to be sparse. So what's the error that we have from this pruning is the difference between W times X, the original output, and W hat times X, the output after pruning. So the error that you want to minimize, the pruning error that you want to minimize, is the norm of the distance. So it's the Frobenius norm of W times X minus W hat times X. Which brings us to this optimization problem that we have, which we are going to minimize over the prune weights W hat. We're going to minimize the layer-wise construction or pruning error, but at the same time, we want W hat to be sparse. Depending on what type of sparsity we are considering and working with, the constraint is going to be different. And next, I'm going to cover some of this. So first, let's start with unstructured sparsity. Basically, we want most of the weights to be equal to 0. So for example, we can say that the total number of non-zero coordinates in W is going to be at most k. And unfortunately, it's very difficult to accelerate unstructured sparsity on GPUs. However, if we add a bit more structure, usually it's called semi-structured sparsity or N2M, the idea is that if we look at M consecutive weights, at most N are non-zero. So a special case is 2 to 4 sparsity, which tells us that out of every 4 weights, 2 are non-zero. And so this is going to give us 50% sparsity, half of the weights are going to be 0, but there is some structure. It's not truly unstructured. And interestingly, Ampere and newer NVIDIA GPUs actually have support. They have specialized kernels that allow us to have faster matrix multiplication using 2 to 4 sparse matrices. And in general, we can, it really depends on the setting, but around 15 to 20% end-to-end speed up we can expect from having semi-structured sparsity in the linear layers. And there's actually many, many different algorithms to obtain prune models. For example, SparsGPT, Wanda, DS0, ALPS, and many more. Here, I'm going to quickly review ALPS and what is the mathematical foundation of ALPS. So generally, the idea is that this algorithm has 2 steps. In the first step, our goal is to find which weights are going to be 0 and which weights are going to be non-zero. What is the sparsity mask? And after we fix the sparsity mask, the question is that what are the optimal values for the weights? So for the first step, which is finding the mask, we use an ADMM-based solver. And after we fix the mask, we use a preconditional conjugate gradient to calculate the actual optimal values of the weights. As shown in this picture here, X times W, the original weights, and the prune weights. First, we use ADMM to find the location of non-zeros, the sparsity mask or pattern. And after that, we use a PCG solver to get the actual optimal values of the weights. So let's look at the mathematics a bit here and dive a bit deeper. So let's look at the unstructured sparsities as an example. So we want to minimize the layer-wise pruning error, which we has discussed, is the norm of the distance between W times X and W hat times X, such that the total number of non-zeros in W hat is at most K. This is a very difficult problem to solve. It has a discrete structure. So let us do a reformulation, which basically we define an auxiliary variable, D here, and we minimize over W hat and D. The objective is the same, but now instead of W hat, we want D to be sparse. However, there should be some relationship between D and W hat. So we get a new constraint that says D and W hat are the same. After this reformulation, we form the augmented Lagrangian for this problem, which is given here as L of W hat, D, and V. So we add the Lagrangian term and the quadratic term here, and we have the sparsity constraint as well here. So in the ADMM approach, the idea is that we update the 3 variables here, W hat, D, and V, one by one, and we alternate between updating these 3 variables. So interestingly, if you look at each of these updates, they have very simple closed form solutions, which can be done very efficiently on GPUs. For example, W hat is basically going to be a least squares problem. We can do this very efficiently on GPUs. For the D, it's going to be a projection operator, which is very easy to do. And for V, it's going to be a linear update, which is quite easy. So all of these steps can be done very efficiently on GPUs, and this problem can be solved for very large instances. Let's also get some numerical results and get some intuition around this. So here I'm showing some results for the Llama 7D model. On the left, we have the zero-shot accuracy on the Pika dataset. And on the right-hand side, we have the actual pruning layer-wise reconstruction error. And we're varying the value of sparsity. We said as we increase the sparsity, the layer-wise error starts to increase. And at the same time, the zero-shot quality starts to drop, which makes sense. We're pruning more, we're changing the network more, so it is expected. Interestingly, we see that if we're doing a good job optimization, up to some point, like maybe 0.5 or 0.6 sparsity, we don't see that much drop in accuracy. However, as we push further and further for more sparse models, then the accuracy starts to drop quite fast. And this shows that basically it's very important to choose what optimization we do, because better optimization means that we will have a smaller layer-wise pruning error, which also is correlated with better zero-shot accuracy. Next, I want to talk about structured pruning a bit as well. So unlike on structural sparsity, in structural sparsity, we actually think about the components of the model. So for example, if you're looking at the MLP layer, we might want to remove the hidden neurons in a feed-forward MLP layer. As this picture here shows, you want to remove some hidden neurons here. Or if you're thinking about attention mechanism, you might want to remove attention heads from the model. Because we're removing a whole neuron or attention head, this translates into removing rows of these matrices, weight matrices. So there's this structure that comes in from the actual components. And because we get smaller models here, if we prune MLP, we are using the intermediate size of the model. And if we remove attention heads, we are reducing the number of attention heads. We get a smaller model, and then this can be accelerated on any device, basically, which is quite flexible. Again, here I'm going to discuss Oscar, which is a layer-wise structured pruning approach. Again, very similarly to the case of unstructured, we use a layer-wise pruning approach. Here, H is the output of some component. For example, if you are pruning MLP layers, this can be the output of the MLP block. Or if you're thinking about the attention mechanism, this can be the output of the attention block. And we are looking at the difference between the original and prune models output. And we want to minimize the overall error average over the samples that we have. And there is some constraint that there should be some sparsity constraints on the double matrix. Again, similar to the case of the unstructured sparsity, this is the discrete optimization problem, which can be quite challenging. In Oscar, we discussed some sort of a combinatorial optimization approach that can give us good solutions to this optimization problem. Let us now look at some use cases of pruning in practice and how we can expect it to work. So I'm going to use this example. It's actually a recommender system example. The idea is that we have some user history, and we have pairs of user and item interactions. And now, given a new item, is the user going to take action on that item or not? So for example, here, we want to see that if a user is going to apply to some jobs or not. So we start with giving some instruction to the model that the model job is to decide if the user is going to apply or not. Then we usually give the member profile. So here, for example, the current position is software engineer at Google. And then we have some historical data that this member has applied to some jobs or has viewed some jobs but did not apply. And now the question is that, is the user going to apply to this new job at, for example, a software engineer in this company? And the model is going to give us a yes or no token. And this is completely text-based. So this is like a prompt that you want to give it to an LLM and decide what's the output. So let us make this a bit more concrete. Let us say that the user profile is denoted by M. And for some time horizon 1 to T, we have pairs of these item interactions. So the item E at time T and the user took some action IT. So given the instruction of the task, the user profile, and all of these historical data, the question is that if we give some new items to the model, ET plus 1 and so on, what is the probability of the action that user will take? And for this example of the recommender system, we're going to look at a decoder-only model because it's just text, truly complete text-based. So here are some numerical examples that can be quite interesting. Let's say we start with the 8B model, it's a llama-based model, and then we prune the MLP layers of this model. So we start with 8B, but then prune to 6.8, 6.4, and finally to 6 billion model. And we look at the AUC of these series of pruned models and how they compare with the base 8B model. And we see that when we are going to 6.8B, you don't see that much drop in accuracy. There's actually basically no drop in accuracy. However, as we push for smaller models, 6.4 and 6B, we see that the AUC starts to go down. However, the nice thing about pruning is that after we do the pruning, we can just go back and do SFT or distillation, which you covered on the pruned model to recover the accuracy that we have lost. So for example, let's take a 6.4B model here and do either SFT or distillation on top of that. We said if you do SFT, the quality drop goes from minus 1.33 to minus 0.47%. And if you do distillation, it is even more effective to recover the quality, and it's basically pretty much the same quality as the 8B model. So we can go from 8B to 6.4B, basically with no quality loss in this case. We can even take it further. We can also prune MLP and attention at the same time. So here we are starting from a base 3B model. We prune the MLP, which brings us to 2.4B. But after that, we push and we prune the attention heads as well. We see that when we do attention pruning, it brings us to 2.1B parameters, and it gives us around 1% drop in the AUC. However, again, we can go do distillation after the pruning to recover the accuracy, and we see that when we do the distillation, let's see there's no difference in the AUC. So we can go from 3B to 2.1B, basically with minimal drop in the accuracy. Next, we have to discuss that what data we use for pruning, because there is the calibration set that we use for pruning. And in general, we can either use open source data or we can use in-domain task specific data. And our findings has been that it's usually better to use in-domain data. For example, in this plot here, we compare for the 6.4B model that we discussed, which is pruned from 8B. We see that we can use C4 open source data, or we can use in-domain data, and we can use either 1,000 1K samples, 4K samples, and let's say 350 and 700. We see that when we are using C4 data, when we add more data points, the drop in accuracy is smaller, which really tells us that we need to add more data when we do the pruning. However, when we go to in-domain data, the drop actually becomes much smaller. So both, and then we add even more data, it's like very small drop in accuracy. So basically, the lesson is that we need both in-domain data and we need a lot of we need more samples. Both of them help us to reduce the drop in accuracy. And now let's say that we obtain this smaller model. The question is that what can we gain from here in terms of inference speed? So we could discuss about the profiling. We can do profiling on these models and see how they compare. And here we have two different models, a 3B model and a 2.1B model at different context lengths, 16K and 32K. And we are looking at the latency of one transformer block here. And we have three main components of our latency here. There's attention mechanism, there's the MLP block, and there is the R-reduced GPU communication overhead. And we see that as we increase the context lengths, the attention latency becomes much larger, like this blue color here. And we see that as we prune the model, recall that the 2.1B model has been pruned from the 3B. We see that both the time for attention and MLP goes down. Especially at 32K, we see that the attention, because it's the main bottleneck, pruning the attention helps us to reduce the latency quite a bit here. Which shows us that basically, in practice, we should think about what is the actual bottleneck and then go after that and try to prune that mechanism or that block to reduce the latency and TTFD in this case. Finally, I want to talk about quantization a bit. Basically, the idea is that we can we discuss quantization for training and also inference. We can quantize the model, we can quantize the weights to lower precision, or we can also quantize the weights and activations at the same time to lower precision. we can do int quantization, and also more recently on copper GPUs, we have floating point or FP8 quantization supported for inference and training as well. So the question is that how they compare? Should we quantize the weight? Should we quantize weight and activation? Should we quantize to 8-bit or 4-bit? In terms of speed, I have some quick comparison here. We're looking at Llama 8B model, Llama 3 8B, and these are, we're looking at different hardware, the H100 GPU and A100 GPU. And we're looking at the TTFT, time to the first token, and TPOT, time per output token, and different types of quantization and precision. At 16 bits, we see that comparing H100 and A100, the newer GPUs are much faster. So, of course, if we have the money, we should buy the newer GPUs. However, we also can do FP8 quantization natively on H100s. And we see that generally FP8 helps both with TTFT and TPOT, which is nice. However, if you don't have access to FP8, we can do int quantization. We can do weights 8-bit and activation 8-bit int, and we can also do weight 4-bit, but keeping activation at 16. We see that when we do weight and activation quantization, it helps us to reduce TTFT and TPOT, which especially helps for prefill tasks. However, when we do 4-bit quantization, because the activations are kept at 16 bits, so we still have to do quantize to 16-bit the weights, which means that we have to do a bit more compute. So in reality, our TTFT is going to be slower at W4A16 quantization. However, because we are able to save memory, we can increase the throughput of decoding and reduce the TPOT, as we see in this case here. And with this, I give the presentation back to QQ to wrap up this section.
Thanks, Kihan, for walking us through the pruning and quantization techniques. So both of which are incredibly powerful strategies for reducing the model sizes and also speeding up the inference speed. So now, before we move into the system level optimizations, I want to pause for a moment and re-emphasize a very important layer in model level optimizations, which is kernel optimization. So when we talk about the speeding up as a model level, it's not just about reducing the model size. So it's equally important about like how efficiently we can execute the kernels inside the model. So the kernel level optimizations, such as optimized matrix modifications, fused attention kernels, quantized GMMs, and reduce the memory copy and movement, are absolutely critical to unblocking the full benefits of pruning, quantization, and model compression. So without kernel level of improvement, so even a pruned or quantized model may not deliver the real latency reductions as we want. So as shown here, like the prefill optimization at the model level must include both architectural designs and also lower level kernel engineering. So the dual focus ensures that we not only make the model smaller, but also make every computation step faster and lighter on the modern hardware. So with that principle in mind, let's now dive back into how we optimize the prefill execution across the systems from the infra stack. So one major challenge during the prefill phase is the pipeline efficiency, often referred to as pipeline bubbles. So in a naive baseline setup, each request is processed sequentially. So the prefill must complete entirely before decode can begin. So different requests have different prompt lengths. So short prompts finish earlier, leaving idle gaps like bubbles in the GPU utilizations. Over time, these bubbles accumulate into a serious inefficiencies, degrading the both latency and also throughput. So chunk prefill is one of the strategies to reduce the memory usage for super long context and also pipeline bubbles. So conceptually, you can think of this like a mini batching from the sequence axis in pipeline parallel training. So instead of a large inefficient unit of work, we break the workflow into fine-grained micro tasks that can overlap perfectly. So by adopting chunk prefill and decode maximal batching at an engine level, so production LLM systems can dramatically boost throughput without changing the model weights or architectures. So another piece that is probably the most important part to optimize the parallelization strategies. So since we have already covered some, and this is also probably a too big topic to discuss, so I want to mention one specific MLA case here. So in MLA, we can adopt a data paradigm for the attention layers and the expert paradigm for the MOE layers. So the technical reason why we don't do the tensor paradigm here is that MLA compress the multi-hat attention structure into some multi-latent attention structure, which reduce all hats into a single compressed KV cache per request. So because the KV cache is compressed into unified representations, we cannot like split it directly as we do in the Euro tensor paradigm to shard across multiple GPUs based on the attention hats. So if we still try to use the tensor paradigm, we would have to replicate or copy the compressed KV caches across devices. So which introduces like heavy communication overhead and also negating the optimization benefits. So therefore, in MLA, especially like DeepSeek R1 type of large models, we suggest to put attention layers to pure data paradigm, where each GPU maintains its own local compressed KV cache without any cross-GPU copying. So the MOE layers then use the expert paradigm, scaling the expert's compute across available GPUs dynamically. So also in some advanced open source repos like SGLong, so it implements each DP worker to handle different type of batches, like prefill, decode, and idle independently. So the attention processed data will be all gathered among all workers before entering the MOE layer. So, and after processing through the MOE, the data will be redistributed back to each worker. So there are some dedicated strategies we can use for predictive ranking tasks with task input. So for example, the first one is called multi-item scoring. So during ranking stage, so one user is associated with multiple items. So the member prefix could be pretty long, and scoring them independently have some overlap on the prefix caching. And also the engine level calling and batching could take some extra overhead. So multi-item scoring leverages the attention kernel changes so that can allow you to concatenate all the items in one prompt so that you can process them at one time. So we can score multiple ranking items of a user in a single one prompt. So another strategy which we call is knock-knock is that when overlap the prefill compute of the user prefix features, we can do like overlapping of the ranking prefill compute with the retrieval stage, so that we can directly leverage the KV cache we got from the prefill stage in the second ranking stage when we got the real item we want to score. So we've finished covering the optimization for the prefill stage. Let's now turn our attention to the second major phase of LLM inference, the decode phase. So decode optimization is a very different problem from prefill optimizations. So in decode, since process is inherently sequential, so making parallelization much harder and become memory bounded. So the two main goals for decode optimizations are minimizing the per token latency. We want to make each token generation as fast as possible to deliver responsive user experiences. And another is to maintaining the throughput across multiple users. So to address these challenges, the decode optimization focuses on the techniques like speculative decodings, attention and KV cache management, and customize lightweight kernels for fast sampling, attention, and final layer computations, etc. So in the following sections, we'll walk through each of those techniques and how they allow us to push decoding performance closer to the real time, even at a very large scale. The first type of model level optimization is to explore fundamental changes on the model architecture itself. So let me briefly highlight three emerging approaches. So the first one is linear attention or state space models. So traditional transformers have a quadratic complexity in the sequence length due to the full attention computations. So linear attention method approximate attention in a way that reduces computation from quadratic to linear, making it much more scalable for long sequences and fast decoding. So it offers both lower memory consumption and computational cost compared to the standard attention. So SSM variants like Mamba or RedNet are showing like strong potential for faster inference without sacrificing too much accuracy. So MLA, like multi-head latent attention with weight absorption, is another way that we can use to optimize the decoding stage. So in MLA models, the standard multi-head attention is compressed into lower dimensions, combined with the techniques like weight absorptions, where multiple weight matrices are pre-computed and fused So it enables fast attention computation during the decode stage. So this is especially effective when combining with the NOPE, the no positional encoding structures. And there are some like rope structures which we still need to leverage the original KV cache management and computation. So a newer, more radical idea is to replace the traditional autoregressive decoding paradigm altogether. So instead of generating one token at a time, so we try to use diffusion LLMs, which is a diffusion-based LLM that generates a full sequence in a non-sequential manner. So it using like iterative refinement steps like remasking, similar to diffusion model envision. This can potentially dramatically reduce the decoding steps while still like have comparable performance. So opening a path to like do like parallel sequence generation rather than like sequence token by token decoding. So while diffusion LLMs are still in a very early stage of research explorations, they offer some exciting possibilities for fundamentally faster generation. So in summary, this architectural innovations represents promising new directions to break through the foundational decode bottlenecks of standard transformer models. So one of the most important system level innovations for decode acceleration is the speculative decoding. So in some standard incremental decoding, so the model generates one token at a time. So each token is decoding fully to on all previous tokens. So this can be a strict bottleneck for the sequence generations. And each step must wait for the previous step to be all finished in order to execute the next step. So in sequential speculative decodings, we have a draft model, which is usually much smaller and could be a quantized models or selected from the original model to prune it on it to generate some draft tokens. And then we send to the original main models to do a one-time verifications. And depending on how many tokens we accept based on these verifications, we can directly extend the original models and also extend the draft models in order to do faster decoding. So Medusa proposed another multi-hat speculations, where the multiple speculative paths are generated simultaneously from multiple trained final projection hats. So this needs an extra training on the original models where you have to add some extra projection hat for each of the generation tokens. But you are able to have multiple tokens generated at the same time during inference and using the original model to verify it and accept those that is satisfied and the same as the original model generated. So finally, building on all these ideas, Eagle introduced a tree-structured speculative decoding, where instead of like doing like thinking linearly, so it can like use the draft model to generate the tree-structured drafts, and then like the verifier can decide which tree paths are essentially like have higher probability to be generated, and then like do a verification on the promising tree passes in order to select the one tree path that satisfies the original needs and which is aligned with the original model output. So another major bottleneck during decoding comes from the KV cache itself. So as we generate longer and longer sequences, the KV cache grows proportionally, which consumes a lot of memory and more bandwidth, and also like more lookup times during the decoding phase. So naturally, there has been a lot of research focused on the optimizing the KV cache usage from both system side and model sides. So here we focus on the model level KV cache optimizations. So the first idea is to do the compressions. So for example, KV is a promising method, which we quantize the KV cache into lower bits, where the key caches, we use the channel level compressions, quantizations, and for the value, we do like per token quantizations. So this is based on the property we can analyze from the key cache tensors and also the V-cache tensors. So there are also some other type of techniques like layer sharing or skipping or exiting that we can directly do fast prefill together with fast decodings, and also reduce the KV cache sizes that we want to store either in the GPU memory, CPU memory, or offloading to the disk level. So, so far we've discussed the major optimizations at the model and the KV cache levels. So, and there is one more critical layer to optimize, which is the small operations that happens around each token generations. So this may seem minor individually, but they can add up quickly during the decoding phase, especially in large-scale deployments. Let's walk through them one by one. So the first one is the tokenization, sampling, detokenization, and also some constraint generation. So every generated tokens needs to be detokened into text or sampled based on the probability distributions. So sometimes we apply some constraints like avoiding certain stop words. So although these are lightweighted operations individually, but doing them thousands of times per request introduce like real overhead. So efficiently, so we can do some batch tokenizations and sampling, do some batch sampling, like a sampling process with some efficient kernels together. So the second way is to do some CUDA graph and torch compile. So with CUDA graph captured in advance for some small batches, we can do the decoding much faster, usually like 2 times or 3 times faster for no matter like Llama 3B models or like DeepSeek R1. So essentially the CUDA graph allows us to capture and replay the entire execution flows on GPU directly and avoiding some CPU intervention between the every kernel launch. Torch compile, on the other hand, also optimize the model graph just in time. Although the torch compile time, you have to afford some pre-compute and also the model launching time overhead when you do those. Some other optimizations, including those collective optimizations over overhead reductions. So in multi-GPU serving environments, we often need to like do the synchronization of the KV cache updates or the attention output across the GPUs. So traditional rin or reduce method are pretty bandwidth efficient, but requires sequential communication hoops. So in latency sensitive decode settings, some newer strategies like one-shot reduce, which broadcasting only fewer times, can significantly reduce the collective overhead. So this becomes like critical as batch sizes or model parallelism degrees grows larger in the practical applications. There are other optimizations, including like scheduling optimizations, and also like we can do some KV cache management and reloading accelerations, which requires some like file system level optimization and supports. So this is worth to point out, but could be hard to really integrate it often to the company existing infrastructure. So in short, every token journey involves more than just model compute. So from tokenization to sampling, from collective reduce to scheduling. So we need the careful fine-grained optimizations to truly achieve fast and efficient LLM decoding. So now let me hand over to Aman to talk about some future challenges and directions that we can explore.
Thank you, QQ. So since we covered a lot of topics, let's summarize in terms of what future directions we can take broadly. So let me talk about training first. So for training, as you already mentioned, data plays a huge role, and selecting the right data samples and using synthetic data wherever possible to close domain gaps is something that has a rich scope and is an active area of research. And as Kehan mentioned already, for compressing models during training, you need to interleave pruning, quantization, and distillation so that you're able to compensate for accuracy loss and still get a very high quality model, which works really well for latency sensitive use cases or resource intensive use cases. The third thing is alignment and reasoning at scale. With DeepSeek R1 and other algorithms, it's clear that post-training is a very rich area, and most of the most exciting work in the last 1 year or so has been on the post-training phase. So how can we integrate RLHF or DPO into extensive offline preference data? And how can we create better reward models for both alignment and reasoning? So far, reasoning has been able to find great reward models for coding and math because the reward signal is very clear there. How do you find reward for other domains is an area of research. Number 4, mixture of experts and LoRa. So as we know, mixture of experts allow you to have a very large model, but have the latency or serving cost of a smaller model. So this is popularized by DeepSeek and Mistral, and this is something that continues to be relevant and important. And using LoRa and related techniques to reduce fine-tuning expenses is also something top of mind for us. Finally, based on what Xiao and QQ talked about, kernel first compiler code design, you need to think about the flops and memory footprint of your code. You can no longer get away with just writing Python code and ensuring that things happen optimally. You need to think through all parts of the stack, and that's also something DeepSeek made very relevant with the recent R1 release. And this is something that's top of mind for us. Now, talking about inference, so we know that from quantization, 4-bit quantization works really well, but how can we go even lower, or use mixed precision quantization, or related techniques? That's something that's top of mind for deploying these models. And Kehan talked about sparsity. I won't repeat too much, but having structured sparsity as well as semi-structured sparsity is critical to have models that are good at inference speed. Uh, Third, personalized on-device inference. You need to deploy smaller distilled models to client devices. This is something Apple already does with their foundation model on the iPhone. We'll see more and more such use cases. Like today, Q13 was launched, which is 0.6B. So we expect smaller models to make their way to on-device inference or client devices very, very soon. Finally, QQ talked about speculative decoding and KV cache, etc. So as we see LLMs and GenAI taking more and more use cases with higher load and higher, uh, uh, requests per second, a lot of techniques like KV cache sharing across users will be critical in helping scale these workloads. And finally, this is something we did not discuss, but how do you work towards sustainability and renewable energy? You want to distribute inference workloads across regions based on energy availability and data center utilization. That's something we did not really cover in this tutorial. So that's everything we have to say. We just would like to acknowledge our partners. There are several teams that make LLMs happen at LinkedIn, including Core AI, Talent Market, Knowledge Marketplace, Ads, Flagship Horizontals, and the AI platform. Would like to thank Satya Kirti, who's our optimization tech lead, and Parag Agarwal and our collaborators from Geist. Thank you so much for listening. We're very happy to be able to give this talk. We'll be very happy to take questions if you have any. You can also email us. So let me just re-show the slide for our emails. What was there? Yep, that's our email, aifoptimization@linkedin.com. That's the QR code for the website. All the slides are already linked there. All the resources are already on the website. Happy to take any feedback. And if there are any live questions, we can take them now.
Any questions?
Cool. If there are no questions, thank you so much. This is great.
Thank you.
Thank you for helping organize. I know this wasn't easy with us presenting remotely. Really appreciate all your patience.
No worries.